So let's begin the remaining topics. So keyboard interrupt processing. So this is all about keyboard. So this is keyboard scan codes. You don't need to remember any of this, just for your information here. And if we press some status key, so if the interrupt was caused by a status key like shift, numlock, control, etc., then keyboard status bits that are set in these addresses, these two addresses. But if the interrupt was caused by a character key like A B C D or 1 2 3 4, then corresponding ASCII code is loaded into keyboard buffer. So main thing is just that you need to know if it's a status key, then the status bits are saved here. But if it's character key, then it's saved in keyboard buffer. This status key, memory bytes, status bits, this is the address, and it is for 2 bytes. It is made up of 2 bytes, and this is address for keyboard buffer. You don't need to remember any of this. So yeah, this is the status bits. This will be most probably a question in test. So what does it mean here? So this is the address of this status bits. Again, 8 bits, 1 byte. This is also 8 bits, so 1 byte. So that's how it makes up 2 bytes of content. So what it means. So for instance, if insert is on, this bit will be 1. If caps lock is on, this bit will be 1. If caps lock is off, then this bit will be 0. So it just means on or off, or you can see if control is down, that means it's 1. If its control is not down, that means that this bit is 0. And this is about status bits, and this is about keyboard buffer. So it is made up of 32 bytes. This is the address of it, and the head, there are 2 pointers. There is a head pointer and then there is a tail pointer. If the value of head pointer is equal to tail pointer, that means the buffer is empty, and each 2 bytes of the buffer item contains ASCII code, scan code, or extend. For instance, this is the buffer, 32 bytes. I will not make all of them. Let's just suppose that this is if there is no buffer, that means this is head pointer as well as tail pointer. So this buffer is basically empty. But if we, for instance, we just press 1, so the head pointer will be pointed here and the tail pointer will point now here. That means that buffer is not empty. That means something is here. And as I said, if we click 1, what happens is it writes its ASCII code down, and where's the scan code? These are the scan codes basically. So key has the scan code this. Yeah. So if I press 1, where is 1? Key, well, this one. So that means scan code is 2 here. So key is 1, so scan code is 2. That means here in each 2 bytes of the buffer. So this byte will be ASCII code of 1, which I think is 31H, not sure. And here it will be the scan code which we just saw, which is 1 or exclamation point, which is 2. That's how this will work. That's how when we press some character key like 1, that's how it is saved. But there is one more thing, extended code. Let's just suppose here we inputted. So let's just suppose we inputted 2 things here. This was of course this will be head pointer, then this will be tail pointer, and this is 2 bytes, and here it will be the ASCII code, and again it depends. Here it says or, and what does it mean is that if this character that we inputted is, for instance, we did shift plus A. If it's a combination, that means this extended code will be used. But if it's not a combination, just one key, that means that this will be used. That's the only difference. So for instance, if I press shift plus A, if I press A here it will be ASCII code and scan code. If I press caps lock A here, then the extended code will be used. So that's basically about keyboard buffer. This is the code that we will study because it's also as one of the sample questions. So here this is all is the code beginning. It's not important, but I wouldn't explain it because they won't ask any of this. Yeah, this all of this is done in 16-bit environment. All of this is done in 16-bit environment, so that's the reason you wouldn't see any of the registers which are 32 bits. So EAX you wouldn't see, EVX you wouldn't see. So 32 bits is not used at all here in this, because this code is just for 16-bit environment. So EAX, EVX, ECX, EDX, they are not here. Only the 16-bit, half of these big registers. So AX, you can see BX, you can see ES, you can see AL, you can see DX. So just half of the registers are used in 16-bit environment. So again, here that data there, here the variables are defined. Byte, press any key or escape to exit. This is just the message. And 13, then 13 means here that we want to move to the first character. So for instance, if we print this message, what will happen is that this message will be printed and the cursor will be moved on uh, depending on these. So 13 means the cursor will move on to the beginning of the line, and 10 means that the cursor will move to the next line. So the combination of this means is basically that you will start the next line and will be at the first character. And dollar means that the message ends. So this is how it's defined. And again, byte means every character is defined as specific byte. And this is the code startup. So first of all, this move AH. So this you don't need to remember, but this is basically how messages are printed on screen using interrupt. So move AH to 9 and to DX whatever the message is. So offset of message in it. So offset means the address basically, address of the text. Function number 9 and system call to display text. This is all system thing. You don't need to remember any of this. But this is just to print the message, and after this, we XOR BX. That means we are making it empty. Move ES BX. So we are moving to ES the value of BX. So let's write it down. So BX was, we made it 0, and then we moved this BX value, copied this BX value to ES. That means ES is 0. And one question here can be that why can't you just do like XOR ES ES? That doesn't work. We have to move into ES value from one of the registers. So that's why we do this. So XOR BX, ES BX, and then we have move to AL. So AL will become now ES 0417H. This might not be familiar, but ES is 0. So 00. Now this might become familiar. What is this? This is the interrupt vector. Again, this was calculated. This is the hexadecimal of that would need some calculations. It would take time, but yeah, this is if we convert this into decimal form and divide it by 4, that whatever we get. So we convert it into hexadecimal and we convert it into binary and we divide it by 4. What will it do? It will give us the interrupt number for this interrupt vector. So for instance, if I say 0009H, this is the interrupt vector. And if I tell you to find the interrupt number, or I would say 9, not 9, 6, 2, 4. So if I say this is the interrupt vector and find the interrupt number for this vector, then what will we do? We will convert this into decimal. And how to convert this into decimal? Again, very basics. So this is 0, so we don't need to. So 4 times 16 power 0 is 4. 2 times 16 power 1 is 32. 32 plus 4 is 36. So this is the decimal value. And if you remember, we divide this decimal value to 4 and we get the interrupt number, so 9. So we studied in the opposite way, opposite direction, from how to get from interrupt number to interrupt vector. Now it's opposite, how to get from interrupt vector to interrupt number. It's just the exact steps, but in opposite manner. So this instruction basically gives the address, this 0000417, which is the interrupt vector, and if you remember this interrupt vector, this address is of This address is for here 000417. That means that this address is of keyboard status bits. So if we continue now, so now what we are doing is we are testing. So what does test do? Again, this instruction was explained in the first videos for midterm test one. And so first of all, what is and? What is and instruction? What does and do? So for instance, if we have 0, 0, 0, 0, 1, 0, 0, 1, yeah, and we do and with this value of 1, 0, 0, 1, 1, 0, 0. And what and does is it turns true only if both of the values are 1. So, or basically you can call it a bitwise multiplier. 1 times 0 is 0, 0, 0. This will be 1. So 1 and 1. That's why it's 1. So 0, 0, 0, and 0. That's what AND does. And test also does the exact same thing. The only thing test does extra is that it does not print the, there is no result for it, and there is no, there is one extra thing is 0. So it sets the flag 0. So if the result is 0, so if the result is 0, 0, 0, 0, 0, all zeros, that then it sets the flag J0 to 1. That's how this test works. So what we are doing here basically is that we are testing 0, 0, 0, 0, 0, 1, 0, 0, B. Now if we go back to this address, the 4417H, this was this address. And if we look at all the bytes, so this is the 1, 2, 3 from here. So 1, 2, 3. So if we see here, control down. So what this is checking is that control is down or not. That's what it's checking. So test, we are testing at this address. We are testing at this address if control key is down or not. So that's why we do this, is because this will basically tell us if the result is 0. If the result is 0, that means control is key is not down. But if the result is something other than 0, that means that control key is down. So if the result is 0, that basically means that this the address is, for instance, you can say 111 1000. So you can say that. Now you can see if we do test, what will be the result for this? So 0 multiply, this is just multiplying, so we are multiplying. Yeah, everything is 0. That means that control key is not pressed. But if we do this test with, for instance, let's make this 1 now, and what will be the result now? 0, 0, 0, 0, 0. Now we multiply this again, so 1, 0, 0. Now this is not 0. That's what we are testing. So that's how it tests if control key is down or not. So if it's 0, that means it's not no control. So 0, that means no control key is not down. That means we jump to the label no control. But if control key is down, that means we will do the rest. The code for that is will be done here. So basically, mov dx. This is basically doing printing. This control key is down, and yeah, this is for printing. So this both of the instructions are for printing. So yeah, so if the control key is down, this will be executed. If it's not down, that means that this test is 0. It will jump and move forward. So this is how this code works. And one of the questions from the sample task is here. So if we, yeah, here it is. So a program is given to show alt and left shift keys are down if held at when the code is executed. Okay. So what we are trying to do is that we need to give this output. So alt and left shift keys are down when these two are um, alt and left shift are down. That means out of this left shift, is 1. So let's write left shift, and alt is also down. So alt is, yeah, so like this, 0 0 0. So in the question, whatever it says, alt and left shift, that's how we will write it. So if alt and left shift keys are down, that will be the that's how we will test it. That's how we will put 1 at those binary values. So the testing will be done. First of all, you can see that input, everything is done here, move bx, and we put es bx. So if you notice here again, when we put bx and es, we also have to put the offset value. So we can see that this is the address for these two keys that are down are in the this address. That's why we will put this address inside of our register. So let's start with this. So move. So what we are trying to get is move to AL, the value ES. That's the ES, or we can say extra segment register ES, and here it will be the address 0417H. So move to AL, this address, and then we test this address with this binary value, which will test basically if uh, so 1 is here, so this alt and left shift is down, so 1010, and this is in bytes. Yep, so this is the two instructions basically. Okay, so we tested it, and then one more instruction that there should be is jump instruction. So if it is there, if those left shift and alt keys are down, then these will be executed. So we just basically need to write a jump that goes here. So jump not down. But how will we do that? We will do that. So if these are down, that means that this result will not be 0. It will be exactly like this. So 0 0 0 1 0 1 0. So if they are down, this will be the result. They are not down, result will be all zeros, which is basically 0. So if the result is 0, we jump to not down. These are the three instructions that we will need to put here. Here you can see slightly different, but they do the exact same thing. You can write any of these, they do the exact same thing. But main thing to remember is that you should just try to remember this, that first we move this register value to AL, and then we test it with the keys that we want to be down. So if the question was about insert key, then the test will be done with the bytes. So 1 is down, so 100, and all everything else 0. And if it was insert key and caps lock key, that means that this will be instead 1. That's how this is testing will be done. And again here, if it will not be down, that's when we will jump to this instruction. So this is, I would say, slightly easier than this, but they do the exact same thing. Okay, that's basically it about keyboards. I would not go further because it gets very complex. And in the sample test paper, sample tasks, it says that there will be keyboard basics. That's why I will not go into detail in any of this. Okay, so this is all about keyboards. Now let's move on to timer. Let's move on to timer. And okay, let's move on to timer, interrupt, timer and sound. Okay, and this is basically PC, timer and sound, exactly. So timer and sound. How does this? Timer and sound. Timer interrupt. So timer interrupt worked with tick system. So it's like one timer tick is 55 milliseconds. So if we will tell the computer to, I don't know, wait for 10 ticks, or I should say 20 ticks. 20 ticks, that means that we are telling it to basically wait for 55 times 20. And if we calculate this, it will be 110 milliseconds. And if we convert this into seconds, and of course, 1 millisecond is 1000 of a second, so it will be 1.1 seconds. So that's how timer interrupt works. It works with tick system, and of course, the timer interrupt is IRQ0 and 55 milliseconds increments the system counter 4-byte integer value at this address by 1. Okay, the main thing here is this. So increment CS ticks, compare CS ticks with 182, that is 10 seconds. So that's the main thing that you need to know, that we compare the ticks constantly with 182. As soon as 182 ticks are reached, we uh, stop, because this function is executed when it is below. So if ticks are below 182, that's when the function is executed. This is all from video memory. You don't need to know any of this. Timer is activated. Timer interrupt vector 3-point address. Wait, no, you don't need to know any of this for basics. Okay, so again, IRQ0 is interval timer. IRQ1 was keyboard. Yeah, that's basically the most the biggest thing from timer. Or you can say that IRQ0 is most probably, if we get question from timer interrupt, it will be theoretical, I think. IRQ0, and yeah, I don't think we will need to remember any of this. System can be current time. Yeah, that's all from the timer interrupt. Let's go to sound directly. Sound interrupt. The main thing to learn about sound interrupt is that, so the maximum sound frequency that can be produced is this. So 119,318 hertz. And if we want to get, so if we want to get a sound of 1000 hertz, or let's just say 100 hertz, that means that in the latch register, or you can say just the register that we need to get the sound, the register counter value will be 119. So when we divide this by this, so 11931.82, but we ignore everything after this point. So this is the value. This will be the value for the counter. Similarly here, this is AX is the counter register here, and if we want value 1000 hertz, a sound of 1000 hertz, that means we will divide this overall value by this 1000, and we will, of course, 4 digits we will get. Will There are 3 zeros, so we will remove the 3 last digits. So 1193 will be the counter value. Similarly, there is a question related to this in here. So 10,000 hertz. So PIT is used to generate a time and output sound. What value must be loaded to the counter to generate output sound of 10,000 hertz? So again, this all is mentioned. You don't need to remember any of this. So 119312 hertz is mentioned. And if we want 10,000 hertz of sound, what we need to do is we divide this by 10,000. 10,000 has 1, 2, 3, 4 digits, or basically we can just remove however many the zeros are. We just remove it and we get answer 119. That's how this one works. That's basically it from sound, I guess. Yep, these are very, very basics. can even remember how PIT works. So set command register bits to access channel 2 to provide desired settings. So these are the desired settings. Don't need to really know any of this because it's complex. And then calculate the value of counter register. That's the main thing. Generate 1000 hertz. Set the counter register value. Open both gates to start sound. So this is the main thing, that we need to open the gates and then close them for sound to stop. So this is how this works. So in or out, this is how basically this looks. To open the gate, this is how it's always done. And to close the gate, we do and the opposite bits. So all of these opposite bits and 0, 0. Here as well, port 61H. This is the port 61H, right? Yeah, 61H. And yeah, these two bits are basically to opening the gate. This specifically, and this for the sound. This is how uh, sound is produced. So first of all, we count how many times it will be done, how many times the counter will go off, and then we open the gates, and then we set a timer or run a code for a few seconds, and then we close the gates. And this is how we close the gates, and this is how we open the gates, or this is the only main thing, and this that we studied. And one last thing is a video adapter. The only main thing that we will learn from video mode is there are two types of video modes, the text modes and graphic modes. So VGA text mode. How does VGA text mode work? Yeah, this is the main thing that we need to study from here. Specifically, VGA text mode, text VGA. So when we need to find an offset for where we want the text to come to show, because to computer we cannot tell it directly that we want to, for instance, print here, I don't know, print here. So what happens is that we give it an offset value. So to calculate this offset value, we do this 2 times 80, or 2 times of 80 times row minus 1 and column minus 1. So if I want to print a symbol on the first row, so basically every the screen is divided into rows and columns so that we can tell the computer to print where exactly we want to get these text output. So if we want in the first row, and for instance, column number, I did write this here, just a second, column minus 1. So if I want to output text in the first row, what will I do is we just put 1 minus 1. So this will become 0, 2 times 0 plus, and I want to input in the, for instance, first column. So this offset value will be 2. That's the main thing that basically is tested in the sample questions as well. Just like this, so row minus 1. Yeah, that's basically really all basics about it. There are much more details, can go much more deeper, but there is not enough time for that. So I will just cover the basics. So in the test as well, this is the task number 4. So you can see, so there are 25 rows, 80 symbols per row, 16 colors. You don't need to know any of this. Main thing to know is two letters OK should be displayed in the first row. So first row, the screen, starting from the position 40. That means the row is 1, first row, and column is 40. So starting from the position 40. So here, what we are doing is basically write one or more missing instructions in the code line to assign the value register AX to have the letters on the screen in the required position. So yeah, this is all the basic code how to print, and here we have to give it the address where to print. So to AX register, we have to move to AX, and now we need to give that offset value, that address, what we need to print, where we need to print. And to get that, we put this in everything into this formula. So row minus one, so 2 times row minus 1, 1 minus 1 will be 0, so this will be 0, plus column is 40, 40 minus 1 is 39, this answer will be 78. That's why the answer here is move to X 78. So this is basically about VGA text mode. Let's go to now VGA graphics mode. So now instead of dealing with the rows and columns, we will deal with pixels. So VGA graphics mode. In VGA graphics mode, what happens is the main thing to know is that there are 4 display planes. There are 4 planes, 1, 2, 3, 4, something like this. And we need to give each of the plane some bit value to display a specific color. For instance, here 1010 will give us bright green color, something like this. The 4 planes, and these planes are only imaginary. They represent the data structure in the memory to understand the principal operation. They are not physical overlays. It's not physical, it's just to understand. And so main thing to know is that there are 4 planes. And then planes, first light. Here as well, we should basically study what this means. Calculate offset of the byte in the video memory. So there are 4 planes, just keep that in mind. Write 1 pixel on the VGA graphics mode at this resolution and 3 parameters. So calculate offset. Offset again, this offset has different formula again. 80 times y plus x divided by 8. And bit num value also, you should try to remember. So bit num is done 7 minus x percentage of 8. So this is not percentage, but the remainder left after we divide this by 8. So for example, if x is 10 and y is 1, offset will be 80 times y, so 80 plus x divided by 8. So 10 divided by 8 is basically 1 point something, but we cannot write in decimals, so it will stay 81. And the bit num value, so this is for offset, this is for bit num. So if they in the exam they say that you need to calculate the offset value, how will we calculate the offset value? Then we need to do, yeah, we need to calculate like this. So bit num, so 7 minus x is 10, so 10 divided by 8. The remainder is 2, so that's why this will be 2. 7 minus 2 is 5. So yeah, here we basically do the same thing, but in assembly language. This is all very complex. So let's just focus on here. That's the main thing that I want to discuss is VGA graphics mode. Um, so here it's given that there are, okay, this is all simple. How many bytes? This is all this simple description how VGA graphics mode works. And the main thing here is how many bytes are used to store information in video memory about one horizontal line of 32 green color pixels. So 32 pixels, there are 32 pixels. Main thing to know is 1 byte saves 8 pixels because it has because each pixel you can say is a pixel is each pixel is represented by a bit. The 32 pixels are represented by 32 bits, and each byte has 8 bits. That's why every byte is represented by 8 pixels. So what we want to do is we want to represent 32 pixels. So of course, there will be 4 bytes representing 32 pixels. But remember, there are 4 planes. So these 4 bytes will be active in each plane. So overall, there will be 4 times 4, 16 bytes active in the video memory. So how many bytes are used to store information? For 32 pixels, the color doesn't matter here, 16. So that's what it's also explained here to, yeah. The main thing is just if the pixels will be given, what you need to do is we need to basically 32 pixels are given, we divide it by 8, we get number of bytes, so 4, and we multiply it by 4, so 16. So 4, because there are 4 planes. So that's basically the reason behind it, because there are 4 planes, and yeah, that's how this VGA graphics will have the question about it. So yeah, that's all. We have discussed all the question types that there can be and a bit of basics about every topic. Thank you.